All right, so rain or shine, we have to go. So I counted that we only have 9 more lectures to go. So times really fly very fast. So the last 3 chapters are very important and very complicated. So if you can, don't miss any one of these. You're going to spend more time catching up eventually. So before we start, the third set of homework will be changed from the in-class submissions to traditional homework. So you need to work out these problems, total of 6 of them, and hand it in next Friday, before I start my lecture. So please bring your homework next Friday, finish it, and bring it to me next Friday before the lecture. Okay, so let's move on to chapter 10. Okay, so we are trying to analyze indeterminate structures now. So before introducing techniques to do that, we introduce a few concepts that you can use to simplify your analysis. These concepts are centered around the so-called symmetrical structures. So if you are so lucky that your structures you try to analyze is a symmetrical structures, then you can utilize these concepts to simplify it. So let's define a symmetrical structure first. So what is a symmetrical structure? So the definitions of that is very straightforward. You find so-called symmetrical axis of symmetry. And if you can flip your structures with respect to that axis of symmetry, and you find out that before and after the structures are exactly identical, then it's called symmetrical structure. So here are a few examples of symmetrical structure. So like this is roller support, and hinge there. And the material properties and dimensions are exactly the same on both sides. So the axis of symmetry will be right there, and then if you flip the structures 180 degrees, and the structure will be exactly identical. So that's called symmetrical structure. So more example like that. This is symmetrical structure. So the requirement is the dimension or the geometry, support conditions, and material properties have to be exactly identical on both sides. So like this, hinge and hinge, truss structure, and the layout left and right are exactly identical. So the axis of symmetry will be right in the middle. So if you can flip the structure 180 degrees, they will be the same. And this one, I and 2I, again, hinge and hinge. So axis of symmetry is right in the middle. So no problem. It's very easy to identify whether you have a symmetrical structure or not. Now here, frame structure, very easily identify. It's a symmetrical structure. Frame structure like this, again, symmetrical. Okay, this is indeterminate structures now. They are also this is also a symmetrical structure. Now we are talking about structure only. We're not talking about loading yet. So don't be confused by the loading. So look at this. This is a hinge. This is a roller and roller and roller. So the dimensions and the properties are symmetrical, seems to be symmetrical with respect to the central axis. But there's a hinge support and there's a roller support there. So if you flip the structure 180 degrees, it seems that the supports conditions are not the same. So you have a hinge, you have a roller, flip. Now roller become here, hinge become there. So strictly speaking, this is not a symmetrical structure, strictly speaking. However, if you anticipated that your loading is not contributing to horizontal directions, you only have vertical directions loading, then whether this is a hinge or this is a roller, it doesn't really matter because horizontal, there's no force. So if you consider that, then you can still consider this structure as symmetrical structure. Okay, so how about this one? Well, this one, geometry, dimensions, they are identical on the left and the right. Now, the differences will be the material properties on the left and on the right are different. So if you flip the structure, then you see that it's not going to be a symmetrical, although it appears to be symmetrical from the geometrical and support conditions viewpoints. So you cannot classify this as a symmetrical. So yes, this is. No, this is not. And this is somewhere in the middle, gray area. So it depends on the loadings. So you can classify this as either symmetrical or not symmetrical. Okay, now talk about loadings now. Let's look at the loading. Now, loading also have similar properties. We could have a set of loading which is symmetrical with respect to a particular axis of symmetry. So for instance, this is a structure and the loading is on the left and on the right. If they are positions at the equal distance, and you can flip the structures, then the loading will be flipping together. And if before and after the loading conditions are exactly identical, then it's called symmetrical loads, right? So you flip, become that, so exactly identical, no change. So distributed loads, you flip, nothing changed. Triangle loads, nothing changed. So perfect. This is called symmetrical loads. So these are more examples of symmetrical loads. You rotate the structures 180 degrees, nothing changed. Loading-wise, nothing changed. We call it symmetrical loading. Okay, so two-dimensional wise, this is symmetrical loading. One from the left, one from the right. Right? You change 180 degrees, same. Now, there's another type called anti-symmetrical loading. Anti-symmetrical loading. So what is anti-symmetrical loading? It goes like this. If you have a set of loading, you rotate 180 degrees, and then change signs of the loading, and returns to the original loading conditions, then it's called anti-symmetrical loading. So this is the original loading. So you rotate 180 degrees, becomes like that. So right-hand side goes to the left, left-hand side goes to the right. After that, you change the signs of the loading. So downward become upward, upward become downward. You change the sign, and you noted that the loading conditions becomes the same as the original loading conditions. Then you call this kind of loadings anti-symmetrical loading. Right? You need to do a rotation first, and then change the signs. So take a look at this. So left-hand side is upward, right-hand side is downward. You rotate 180 degrees, so become this and that. Then you change sign, flip sign, and then you've noted that they becomes the original loading. So it's called anti-symmetrical. So here is another example of anti-symmetrical loading. More example for anti-symmetrical loading. So why do we discuss symmetrical structure and symmetrical loading, anti-symmetrical loadings? It's because we can utilize some of these properties to simplify our analysis. Okay, So first, there's a nice property coming out is no matter what kind of loading you have acting on the structures, I can always decompose the loading into summations of symmetrical and anti-symmetrical. Any arbitrary loading, I can always decompose into symmetrical plus anti-symmetrical. So let me show you how you can do this. So this is obviously none. It's not symmetrical, not anti-symmetrical. You know, it's obviously not. So how do I decompose this into summations of symmetrical plus anti-symmetrical? I first divide the loading magnitude by 2. Scale everything by 2. And then do rotations of 180 degrees. Rotate the whole system by 180 degrees. Then I do this plus that. I add these two up. I call this B and this called C. I add these two up, and you notice that it becomes symmetrical loading. And I subtract this two, B minus C. I found out this becomes anti-symmetrical. And if I add this two up, it goes back to the original loading. So that seems to be a magic, right? Original loading is this. Now I will be able to decompose this loading into symmetrical load plus anti-symmetrical load. Any arbitrary loading, I can always do that. Seems like a magic, right? So you want to see that again? So original loading, A. Take that, scale, divided by 2. You get B. And then you do 180 degree rotations. You get C. B plus C, symmetrical. B minus C, anti-symmetrical. And then these two add up. C, C cancel. 2B. 2B is A. So go back to the original. All right? So that's the conclusions. It's very interesting conclusions. I can always decompose any arbitrary loading into summations of symmetrical and anti-symmetrical. Okay, that's interesting. So I can show you a few examples. This is a structure loading, obviously not symmetrical, not anti-symmetrical. So I scale this by 2, flipped 180 degree, sum up, symmetrical load, subtract, anti-symmetrical load, and then add this two up, go back to the original loading. So instead of doing this analysis, I can do this and that. I don't have to do this. I can do this and that. Of course, you need to superimpose the final results. So it's a very important milestone for you. We have basically completed what we want to introduce in the deterministic structure domain. From this point onward, for the remaining part of the class, I will be focusing on indeterminate structure analysis. Indeterminate. That is obviously very important because all the structures that you see around you are indeterminate. So, reminding you, how do you distinguish determinate structure from indeterminate structures? The condition is whether you can solve the structures by equilibrium conditions alone. If you can solve your structures by equilibrium conditions, then that is classified as determinate structures. If not, then it's indeterminate structures. So what is the advantage? What are the advantages of using indeterminate structures? So left-hand side here is a simply supported beam. This is determinate, or you only need equilibriums. On the right-hand side is a clamp beam. Obviously, it's indeterminate. 3 degrees indeterminate structures. So why do we want to have a clamp beam instead of a simply supported beam? The reasons are obvious. The deformations will be smaller. So for instance, under the same loading, the maximum deformation for the simply supported beams will be this much, and for the clamp beam will be this much. So only 1/5. Deformation is only 1/5. Internal bending moment. This is 1/8 of WL squared. This is 1/24 WL squared. So the stress, the bending stress, will be smaller. So the indeterminate structure provides you with a smaller deformations, a smaller internal stresses, which are all positive. Also called fail-safe. Fail-safe. So this is 1995 Oklahoma city bombing. So take a look at the structures there. The bomb exploded right in front of the buildings, kind of cut off the structures like that. About 1/3 of the structures got cut off. And you can see that the remaining part of the structure still stands there. It's called fail-safe. Imagine that if the whole building collapsed because of that, more people will be killed because of that. So this kind of structure has a high degrees of indeterminacies. So usually they can accommodate failures of a few components. So called fail-safe. Now, also they come with disadvantage. It's not all win-win situations. The disadvantage is you're going to see some sort of stresses that is not supposed to be there for determinate structures. So for instance, this is simply supported. There's a hinge there, so simply supported connections. So if I have a settlement, it's quite common for civil engineering to see some sort of settlements. If this point moves down, then because they are determinate structures, so it will not create any effects other than deformations. There will be no bending moment, no internal stresses. Right. So nothing happens material-wise. The only downside of that is the structure is deformed. So you see this deformed shapes come out, but no stress whatsoever inside the structure. But if you have a continual beams like that, then this becomes 1 degree indeterminate structures. So continuity, say that if point B deflect, continuity, say that there must be some bending moment developed. So bending moment then will create internal stresses. So internal stresses is going to pressurize your materials and maybe damage your materials. Okay, so these are the internal stresses developed for indeterminate structures. And thermal expansions. Everybody knows that for highway bridges, long span bridges, you need to have a thermal expansion joint, because once they expand due to the temperature raise, then you're going to see some sort of stress inside your structures, which is not good. So for instance, determinate structures, we don't have that promise. So it's free to expand, no stress whatsoever. But if you confine, make a fixed connection, a fixed support, then the structure cannot expand. So it has to be compressed back to the original positions. Then that will create the so-called thermal stress inside the structures, which is not good to structures. Okay, I think that's about it I want to say. Next, I will be talking about some symmetrical and unsymmetrical concepts. So I'll see you on Friday.